All right, so this week we're going to do something a little bit different. Again, we're going to take a look at graphing. So we're not really going to be solving equations or doing a lot of sketches of triangles and stuff. We're going to be sketching graphs of sine and cosine. Those are the only two functions we're going to focus on. If we had more time, we could look at the graphs of tangent and secant and cosecant and cotangent. But sine and cosine are the easiest two. And I showed you earlier what they look like. Okay. This type of function is called a continuous function because I can ask you to trace along it, and you never would have to lift your pencil, okay, as you trace it. But if I showed you the graph of tangent, okay, which I'll just do in a different color, could you trace that graph in pink without lifting up your pencil? No. All right, so this is what we call, it's not a continuous function, it's a discontinuous function, and you have to constantly keep lifting your pencil every time you want to trace to a new section. Okay, we are not going to look at the graph of tangent or study it at all. Okay? Just the one in red and blue, okay, sine and cosine. And when we graph, we only graph one thing at a time. Okay, I've got three things going on the screen at the same time, but we don't graph three things at once, just one. Okay, and we're going to graph sine and cosine, but there's four basic transformations we can do. Okay, and I mentioned them earlier, but the four again are stretching left and right, stretching up and down, that's 2, shifting left and right, that's 3, and shifting up and down, that's 4. And we'll basically take a look at one transformation each day, except for tomorrow we'll do 2, because the transformations we do tomorrow are very, very easy. The one we do today and the one we do Wednesday, we're just going to do a single transformation. Okay, so the first thing is these two functions, okay, sine and cosine. They're called periodic functions. And the reason they're called periodic, what periodic means is the graph has a pattern to it, okay? And it repeats itself. Okay? There really isn't any other function you studied in algebra that repeats itself. Like if you sketch a parabola, right? When you sketch a parabola, you just get one parabola. It doesn't keep repeating itself and you get a ton of them. You just get one. But with the graph of sine and cosine, okay, here's the kind of the basic idea. You have a graph that looks like that. Okay? If you take that one section, copy it, and put it next to it, okay, you get the next section of your graph. So the graph that I showed you on the calculator, it's basically one section just repeated over and over, just like I did here. Right? It just repeats left and right forever. That one section. So if I make that one section a different color so we can kind of focus on it. Okay, what happens in that one section is we start at 0. We hit some high value, which we'll take a look at what that is. We come back down, we hit a low value, and then we come back up to 0. So what happens is we're going through all the different values you could possibly go through in that one section in red. Okay? When you get to the next section, you're going to go through all the same values again, okay? Forever. You're never going to go any higher than you did. You're never going to go any lower. You're going to go exactly as high and low in every section as you did in the first one. Okay? And that's what I'm writing right here. The y values are going to keep repeating. You're not going to go any higher, and you're not going to go any lower than you did in the first section. Okay, so the y values keep repeating. But you have to go through a certain amount of x values before they repeat. Okay? How many x values do you have to go through? You have to go from here all the way to there. That's how many x values you have to go through. And then the graph will repeat itself. All right, so I'm going to bring up, back on the calculator, the graph of sine. And I want to look at it and see if we can figure out some of the things I just mentioned. How high does it go? How low? And how many values, x values, do we have to go through before the graph repeats? All right, so let's get rid of these other graphs. And I just want to look at the graph of sine. Can anybody tell from where you're sitting, it might be a little small, but how high it looks like that graph goes? Do you know? Yeah, it goes as high as 1. And how about how low? Yep. Yeah, it goes as low as -1. Okay, so the highest and the lowest that the basic graph goes is 1 and -1. The only way I could change that is if I stretch it out or compress it, or I could shift it up and down. But the basic graph is 1 to -1. All right, now the other thing I want to figure out is how long is it to get from here all the way to here? How many x values did we have to go through? Does anybody have an idea of, starting at 0, where we would end in that first section, like that one I have in red right there? Think about on a circle. Right? How many degrees do you have to go through before you get back to where you began? 360. So if we show you what happens when we're at 0, I'm right where the cursor is blinking. Right? If I go all the way to 360, now I'm where it's blinking. So from 0 to 360, that's the amount of degrees you have to go through before the graph repeats itself. After 360, the graph is going to do what you already saw on the screen, right here. Does anybody have a guess at what angle we hit the highest value? Trevor? Did you have a guess? Or 90, yeah. At 90, okay, everything is nicely spaced on the graph. That's where we hit the highest value. How about right in the middle? What angle do you think that? Not 135. I think we're at 0 to 360. What's right in the middle? Okay. Yeah, 180. Okay, we're right in the middle. And then how about that lowest angle? Yeah. 270. So when we talk about graphing a sine function, those are going to be the 4 or 5 key points you need to find. Okay. Where you start, where you stop, the highest, the lowest, and right in the middle. If you can find those 5 points, that's what you need to make a sketch. Okay? So because it's a wave, it's a little more complicated than a line. Okay? With a line, all you need is 2 points and you connect them. Okay? Well, when we graph these, we need a few more than 2 points. We need 5. Okay, that length of that interval that you guys just said was 360 degrees. That's called the period of the function. Okay, it's the number of degrees you have to go through before your function will repeat itself. Now, when you're talking about the period, 0 to 360 degrees, that's the normal period. Okay? If you don't change it, that's how many degrees you have to go through before it repeats. But I could do something like this. And what I've done now is I've really shortened the amount of x values I have to go through before it repeats. Okay, this one is repeating a lot faster. So it's not 0 to 360 degrees to get one cycle anymore. What is it? Well, we'll figure that out later on. But the point is, I can shorten and lengthen that period. And we'll also look at what that would mean for sound. If I were to play a sound like this to you versus a sound like what's on the right, there's a difference in how you would hear it. Okay? Okay, so I'm just saying here what we already said. The basic period of sine and cosine, if you don't do anything to it, just graph it the way it is, it's 360 degrees, or 2 pi radians. Okay, for this week, we got to get used to working more in radians. Okay, we really won't be doing any problems in degrees. Okay, this idea I've already said to you, and I tried to show it to you visually, that if you graph one section of it, after 360 degrees, the graph just repeats itself. Right? That's the picture I had up above with that red section in the middle, and then the black section on the left and right continuing forever. Okay, so when we sketch this on the homework and on the test, you only need to sketch one section, okay, because it does repeat forever. So I'll just have you sketch one section, kind of like what I drew in red. Okay, that's what you would sketch on the homework or on the test. Okay, and there's also another name for a period, okay, or the amount of time it takes for the graph to repeat. And it's a name that's used more in specific trades, okay, like electrical or automotive. Any field that deals with electricity would use this term. So when you have the kind of electricity like you have in this room, not in your car, that's DC, but the kind of electricity in this room is AC. Okay? It operates on a certain voltage, usually like 120 volts. But there's also something else about the electricity that's important. That should be the same in any outlet you measure, at least in the US. Anybody in electrical know what else I'm talking about? Well, amps is kind of how much current you can carry on the circuit. But there's something else about the electricity itself that has to be the same everywhere in the United States. The voltage should always be 120. And what else about alternating current? Yeah?
How the current moves.
I'm not sure what you mean.
Alternating current, the current goes back and forth, the current moves.
Okay, if you looked at a picture of alternating current, it would look something like this. If you had an oscilloscope and you could plug it into the outlet and actually see a picture of the electricity. How many times is it doing this per second? Because it's alternating. It's alternating current. How many times does it alternate per second? Does anyone have a Chromebook charger on?
I do.
Look at your charger. There's a little sticker on it, or there's something on it that says input. And it'll say probably say 120/240, meaning you could use it in Europe. But it'll also say something else besides volts. 2 letters.
There's a lot besides volts and
Anybody see the other thing it says? Under input?
output.
Well, yeah, it says output, but what else does it say under input? Does it say 120?
It says 50 to 60 Hz.
50/60 Hz. What's Hz? Hertz. Okay. This 50 has to do with Europe, okay, or other countries. In the US, every outlet operates at about 60 hertz, okay, and 120 volts. So 60 hertz is how fast the alternating current is oscillating per second, 60 hertz. And you could probably see, I think it says it on here too. Yeah, hertz. Okay, this obviously isn't an electrical current. This is a sound frequency. But sound frequencies are also measured in hertz. How many times does the sound oscillate per second? Okay. We'll hear what happens when you change that hertz, but not today. Yeah?
Why
Why is it different between US and Europe?
I don't know why the electrical infrastructure is different in each country. I guess, I don't really know. I don't know the answer. I know 240 volts uses less electricity, less current. So like if you have an electric stove, if you have electric dryer, those kind of things have a special plug on them. They're not like a regular outlet. It's a much bigger plug. People know what I mean? That's because that's running on 240 volt. And if you double the voltage, you have the amount of current you need to run it. So you actually use less current on 240 volts. So that's why we run our dryers on like 240. If it's an electric, if it's gas, that's totally different. But I don't know why other countries use 50 instead of 60 hertz. But if you plug in something like on the Chromebook charger, it said 50/60, which means it would work fine. You could just take that charger, you could plug it in another country and it would work fine. Some older devices, if they don't say 50/60, if they just say 60, and you try to plug it in, it's going to ruin it, whatever it is. Computer, TV, it would just fry it right away. But a lot of devices now, they're made, most cell phone chargers, you can use them in either country. But there's still one other problem. In the US, outlets kind of look like this. That's kind of the shape, the positive, the negative, and the ground. But in other countries, the outlet also has a different shape. So not only is it a different kind of electricity in the wall, it's a different shape that it plugs into. Some outlets in other countries look like that. They're just two horizontal, like round holes. In Italy, they have one that's 3 holes. So you need an adapter. If you want to plug in like your Chromebook charger, it wouldn't physically fit in the wall in another country. Even though it would work with their electricity, it physically just wouldn't go into the wall. You'd have to get an adapter that allows it to plug in, and then it would work fine. All right. So there is a connection here with electricity and stuff like that. We don't study it too much more, but I just wanted you to see that another name for a period is also called a cycle, and that's exactly what hertz is. Hertz is cycles per second. Okay, so alternating current in the US has a cycle of 60. It alternates 60 times per second. Or at least it should. If you have a generator, sometimes people have like a cheaper generator. It's not really a real good generator. This number, that's 60, might change a little bit. You might see it go up to 62 or down to like 59, 58. And what's going to happen is if you run a motor for a long time that's supposed to run at 60 hertz and you're running it at 62, it'll work, but it's going to overheat eventually. It's not, because the electricity coming from the generator isn't quite right. So that's why some people that buy really, really cheap generators, you got to be careful because you can ruin things that are sensitive, or overheat motors and stuff like that if you use it a long time. Okay, but good generators, they automatically regulate and fix that kind of stuff for you. All right, so when we graph a trig function, as I said, you're going to have to find 5 points. Okay, and I call these like the 5 important points when you're graphing, or the 5 key points, where it starts and stops. Okay, the highest, the lowest, and then the point right in the middle. If you can get those 5 points, you'll be able to make a pretty good sketch. So whenever we graph a transformation of sine and cosine, we have to know where it starts. Okay? We can't figure out where something is going to move to if we don't know where it was originally. So what I'm going to do now is I'm going to give you the original table for sine and cosine. These are the 2 tables that you're going to use on every problem we do this week. They're the starting point for every problem. And then depending on how you transform your function, did you move left, did you move up, what did you do, you're going to adjust the original table. But you've got to start with the original. Okay, I'm going to start with sine first. So the way I think of it is this is kind of broken into 4 sections. 1, 2, 3, 4. Okay, we have those 4 sections. And how many degrees is it to go from the beginning to the end? It's 360, unless we change it. But if we just look at the basic one, it's 0 to 360. So if you divide 360 by 4, that tells you how much each section is that I just traced on that graph. What's 360 divided by 4? 90. Okay, so what we're going to do is graph these points. We're going to make a table. And every point here is 90 degrees apart. In fact, we just went through them on the calculator. 0, 90, 180, 270, 360. Okay. What I've done is I've written out those 4 values I just said, except that's radians instead of degrees. 0, pi over 2, pi, 3 pi over 2, and 2 pi. That's 0, 90, 180, 270, 360. And now what I'm going to do is make it a little smaller. So we can see the graph and try to fill in the y values at the same time. Okay. So I want you to look at this graph when x is 0. Dave, looking at this graph, when we're at 0 for x, what's the y value?
0.
Yeah, it's also 0. Let me make it a little bigger. Okay, so it's 0. Don't worry about cosine yet. We'll do that one after. How about, James, when we get to pi over 2, a quarter of the way through that graph, what's my y value at pi over 2?
I'm not sure. Where's pi over 2?
So pi over 2, so that's all these points that I've marked are those x values in that table. So when we're at pi over 2, what does it look like my y value is? It's the highest.
1.
Yeah, which is 1. I didn't label it, but I can. Okay, so when we get to pi over 2, we're at 1. Ariel, how about when we get to pi?
0.
Yeah, we're back to 0. Okay, 3 pi over 2. Marcos, when I get to 3 pi over 2, what's my y value? Yep, I'm at negative 1. And Gabe, when I get to 2 pi,
0.
I'm back to 0. Yeah, I didn't label it, but okay, when we get to 2 pi, we're back at 0. Okay, so what we just filled out here is the original table for sine. Okay, you really want to make sure you get that table right because you use it on every problem. Okay, now when I graphed sine and cosine on the calculator, were they exactly the same graph? No, one of them was a little off. So we're going to see all these same numbers for y values, but they're all shifted in different spots. Okay, we're going to use the same x values because we want to keep the x values evenly spaced. That's how you can make a nice graph. Pick 5 evenly spaced x values. 0, 90, 180, 270, 360. Okay, that'll give me the highest point, the lowest point, the start point, the stop, and what's exactly in the middle. So we just have to find the y values for cosine. Okay, this time, I'm just going to sketch it on here. All right, so I'm going to do cosine x. Oops. And all right, let's focus on what you need to look at. So let's go. Okay, so that's a wave. Okay, but I'm only focusing on part of it. Okay, I'm just focusing on the 0 to 360 part for cosine. Okay. What's my y value when x is 0 here? Yeah, I'm starting out at the highest value. So I get 1, and then I come down to 0. Okay. And then after 0, what do I hit? At 180, or pi, I hit negative 1. At 3 pi over 2, 0. And then at 2 pi, we're back to 1. So they're exactly the same y values as for sine, but you're starting at 1. Where sine, you start at 0. Okay, any questions on the original table for sine or cosine? Now, does this graph really stop right on the edges of that screen? No, I could zoom, press 3, and that'll zoom out. And now you can see more of it. It looks smaller because I zoomed out. But I'm only having you focus on the section that would normally go from 0 to 360. If you can figure out what happens in that section, well, you could figure out what happens in any section. It's the same thing. Okay? It's the same pattern repeated. Right? Okay, so after you have your original table, then you have to do your transformation. Okay, for every transformation that we do, since we're only doing one transformation at a time, one of the columns will stay the same in the original table, and the other column will change. Okay, and again, the reason is, let's say I decided to take my sine function and shift it up. Just to be simple, I'll say up 1 unit. If you shift something up, what values does that affect? X values or y values? Y's. So if I said to you to shift the sine function up, you're not going to change the x's at all. Those are going to stay exactly the same. You're going to take all the y values, and if you're shifting up, you would add 1 to all of them. You would shift them up 1. Now, if I said to shift something left or right, what values would that affect if you move left and right? That affects the x's. Okay? So if all you're going to do is shift something left, you keep the y's the same. You don't do anything to them. Okay? So that's why I said for every transformation we do, one column will stay the same, and one column will change. Now, this doesn't always have to be true. Okay? If we had more time, we can do 2 transformations at once. I could say take and shift it up 1, and then shift it right 2. And then both columns would change at the same time, because you're shifting up and down and left and right. But in this class, we don't look at multiple transformations at the same time. Okay? Just one transformation per problem. Okay, so everything I've set up until now is pretty much kind of general background stuff that applies to everything we do all week. Okay, so from now through the end of the week, I'm just going to focus on how to do one transformation at a time. So the first transformation I'm going to show you how to do, and the only one we're going to do today, is a phase shift. Okay, so a phase shift, okay, it's what we call a rigid transformation, because all it does is take exactly what you have and slide it left or right. It doesn't do any kind of stretching to it. Okay, and in the program that I have, I can show you a phase shift very, very easily. Okay, so a phase shift looks like this. That's a phase shift. It just takes exactly what you have, it doesn't stretch it, it just pushes it left or pushes it right. Okay? Eventually, if you do enough of a phase shift, you can actually line it right back up with where you started. So you can see that if I shift something 360 degrees off, you can't even tell the difference between that and shifting it 0, because they line back up again. Okay? But usually we don't shift 360 degrees. We do a small shift. We're going to be doing it in radians, but 45 is a common shift. 90, that's one we'll do, and usually 180. I can't really get it exact, but those are the shifts that we do most often. Just because the arithmetic is a little easier. I mean, if you wanted, you could shift something by 136.8 degrees. You can shift any amount you want. It's just the common ones are 45, 90, and 180. Okay, so one really important thing we have to be able to do, okay, by the end of the week is you're going to be given an equation. And you have to decide from the equation I give you which one of the 4 transformations is it. Is he shifting left and right? Is it an up and down? What type is it? Okay, so I'm going to show you the pattern for shifting left and right. Okay, it looks like this. When you do a phase shift, you add or subtract, depends on which way you're shifting, a number inside the parentheses. And that number that you're going to shift by is usually one of 3 numbers. It doesn't have to be, but it's what we do. It's either 45, which would be pi over 4, 90, which would be pi over 2 radians, or 180, which would be pi radians. So you're usually going to see one of those 3 things in this spot. What do you think the difference is between a plus and a minus? Yep.
Which way are you going after?
Yeah, left or right. Plus is going to be one way, minus will be the other. We'll see if we can figure out which way is which. And it doesn't matter if it's sine or cosine. The only difference between a sine and a cosine is when you do the problem, did you start with the table on the left, or did you start with the table on the right? That's the only thing that sine or cosine tells you.
What did you say C was?
C is the number that you're shifting by. A lot of times it's either going to be, I'll just show you an example, pi over 2, pi, or pi over 4. Those are the numbers we usually shift by. And again, it's not because it's the only ones we can do, it's just those are the ones that are most common. You could shift by 93.6 degrees if you want. Right? You can shift by anything, but we don't. Okay, so we got to figure out basically when do we go left and when do we shift right. There's one rule to tell you when you go left and one to tell you when you go right. Does anyone have a guess what plus is going to do? Yeah?
Right.
It's going to shift right? Any other guesses what it could do? Left. It's one of those 2. Let me graph something. Okay, and I'm going to keep it simple. I'm not even going to use pi. I'm just going to use like the numbers, small numbers that aren't pi. Let's take cosine x. And let's take cosine x plus 40. Okay? What I'm doing in this problem is not something you'll normally do. I'm going to shift it 40 degrees. And I want you to see if you can tell me, did I shift it 40 degrees left or right? It's a little small, but I'll make it bigger in a second. If I make it a little bigger, I think it'll be easier to see, or if I just zoom in. But can anybody tell from the blue was the original? Did the red graph shift to the left a little bit, or did it shift to the right? It shifted left. So when I did plus 40, it's shifted to the left. So the rule is, if you have minus, it would shift right. Plus is going to shift left. So that's not what you would normally expect. Okay? You would think on a number line that's not how it works, but that is how it works here. So x minus a value is going to shift right. How much? Well, whatever the value is. Get rid of that. Let me. I'll show you that. I did plus on the screen, but I'll do a minus so you can see it. Okay, and I'm gonna do more of a shift so it's bigger, so it's easier to see. I'm gonna do minus 70. So what I'm going to do is I'm going to shift this 70 degrees, and I'm going to shift it minus means to the right. Okay, let's take a look. There you go. And graph, I can speed it up a little bit. Okay, there's the original. And there's the one in red. So if I make it a little bigger, hopefully you can see that the graph in blue is the original. The one in red has been moved to the right. In this problem, it moved exactly 70 degrees. Okay, so then if you have x plus a value, that's going to shift your graph to the left. So it's kind of the opposite of what you would expect. Okay? And we'll keep that idea in mind. It's the opposite of what you would expect. At least when I think of a number line, positive goes right, negative goes left. Well, it's the opposite of that when you do a shift here. Okay, so last thing we need to figure out is which column is going to stay the same and which column is going to change if we shift things left and right. Okay, so if I shift left and right, what isn't affected at all? The x's or the y's? Think about if you took a coordinate and moved it left, or you move it right, either way. What's not changing as I move left and right?
Your y.
My y's, exactly. Focus on the top of like one of those waves. As I do a phase shift, it slides left and right, but the height doesn't change. Okay, so what that means is you go to your original table, and you can copy the y's down. Whatever the y's are in the original table, those are your y's in your final answer. They don't change. Okay, but if the y's are going to stay the same, then we have to find the new x values. Okay, and there's 5 of them in the original table. And to figure out what's going to happen is the first thing you do is look at what you've added or subtracted, okay, in the problem. Okay, so if I was doing example 1, I would say, okay, in this problem, they have subtracted pi over 2. So I've determined what has been subtracted in this case. They've subtracted pi over 2. And then what I'm going to do is the opposite. Okay, why opposite? We just looked at the graph. Because subtracting is going to move it to the right. How would I shift the graph to the right? I would add something. Okay? Adding would shift to the right. Okay, so it's a little confusing, but then we just got to keep that straight. Look at what's been added or subtracted. In this case, I've subtracted pi over 2. I want you to do the opposite of that to all the original x's. So you see minus pi over 2. I want you to do plus pi over 2 to all the original x's. Okay, out of the 4 transformations that we studied, there's 2 transformations that you have to do the opposite. This is one of them. And then there's 2 transformations that you don't do the opposite. So in your notes, or in your reference sheet for the test, you want to keep it straight. Which transformations do I do the opposite, and which ones don't I do the opposite? Phase shift, you do the opposite. That's one of them. All right, so let's see if we can actually do this problem. Okay, the first thing you'd have to do if you don't know it is look up your original table for sine. Okay, I don't need the cosine table in this problem, just the sine table. Okay, does everybody have what's on the left? Okay. Okay, so what I did is back from the page earlier in the notes, I copied down the sine table just so we have it. And now I'm going to make a new table. I'm going to make a table for this problem. Y equals sine x minus pi over 2. Okay, first thing I have to do is look at this problem and identify what kind of transformation it is. Eventually, your 4 choices are going to be phase shift, vertical shift, period change, or amplitude change. Well, I'm telling you this is a period change. It's the only one I've taught you. What tells me that this is a period change? What's the key when you look at an equation that tells you it's a period change? Do you know? Plus or minus where? In the parentheses. Yeah. If you have a plus or a minus inside parentheses, that's a phase shift. Okay, so when we do a phase shift, one of these columns doesn't change. Riley, which column isn't affected by moving left and right? The y's. So we're going to look at the original table, and we're going to copy down the 5 y values from the original table. Okay. And the way I usually grade this kind of problem on a test is you get 1 point for each x and y value you get right in the table. So if you just know to copy down these y values, you just got 5 points. Okay, now we need our x values. Okay, so I'm going to take all my original x values. I'm going to write them off to the left a little bit so I have room to do some arithmetic. Pi, 3 pi over 2, and 2 pi. What am I going to do to all 5 of those numbers? Gabe? Yes. Remember, phase shift, you've got to do the opposite. I'm going to add pi over 2 to all of them. Okay, and what I'm going to grade is what I write inside that box. All right, first one's not too bad. What's 0 plus pi over 2? Yep, pi over 2. And now, we don't have to worry about it this time, but when you add fractions, what do you have to make sure you have? Yep. You need a common denominator. We already have that here. Okay, so if you add pi over 2 plus another pi over 2, you have, I'm just going to write that over here for a second. I'll squeeze it in here. It's 2 pi over 2, but yeah, what she just said, it reduces to pi. Okay, now the next one, we don't have a common denominator, but what is the common denominator between 1 and 2? 2. So what would you multiply this by to make it a 2? 2. So that means you have to multiply the top by 2 as well. Now you have 2 pi over 2 plus 1 pi over 2. 3 pi over 2. Next one already has a common denominator. 3 pi over 2 plus 1 pi over 2. It would be 4 pi over 2, yep, which reduces to 2 pi. If you just want to write the final answer, that's really what I'm looking for, the 2 pi. And the last one. We need a common denominator again. So Gladdy, what's my common denominator there? Yep, let's apply the bottom and the top by 2. So 2 times 2 gives me 4 pi over 2 plus 1 pi over 2. It's 5 pi over 2. Look at the answers in that column before I reduce them. Does anybody notice a pattern? Yeah. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Anybody know what the next number would be if we were going to find it? Yeah, it would be 6 pi over 2, and then 7 pi over 2, 8 pi over 2, and so on. We don't have to keep going. We stop there. Okay, so you get 1 point for each x and y value. So you get 10 points for that table. 10 points. And now the last step is to graph what's in that table. Okay, the graph I usually just make worth a point or 2, because the graph is easy once you have the table. Okay, the way you want to label your x-axis is with the numbers in the x column, because they're all equally spaced. Remember, they were all equally spaced when we started, and we just shifted them all. So they're still equally spaced. They're just all shifted. Okay. I don't think it's a good idea to number your x-axis 1, 2, 3, 4, 5, 6 in this problem, because you're working with numbers that are messy, like pi over 2. That's 1.57. Pi is 3.14. Okay, so I'm going to number my x-axis using the labels in my table. So this will be pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. If that was in degrees, it would say 0, 90, 180, 270, 360, 450. They're all 90 apart. They're all equally spaced. Okay, what's the highest value that we go? Kelsey? 1. And the lowest? 0 or -1. -1. Now just put those points in that table on that graph. So pi over 2, 0. Pi, you're up at 1. 3 pi over 2, 0. 2 pi is -1. And 5 pi over 2, back to 0. Okay, when you sketch it, try to make it look curved. There's no part of this graph that really turns sharply. Everything should be nice, smooth curve. Just like that. Okay, so there's your graph. Your original would have looked something like this. In red would be the original. In blue is the new one. So what happened is the original moved from here, and it slid to the right, pi over 2, which is exactly what should happen when you subtract. Subtracting should shift it to the right. Okay, so the graph in blue is the final answer. Okay, so I give you 2 points for the graph, and then 10 points for the table. Okay, so a problem like this is usually worth 12 points on the test. Hey, any question on that one? No? Question, Trevor? No? Okay. Take that one, that one. That's it. All right, let's try this one. So this time I'm using the cosine function. So you want to be very careful. You start with the cosine table. Okay, first thing is, I know it's a phase shift. That's the only one I've taught you. But what tells you it's a phase shift? Something about what's in the parentheses. Yep. You what? Yeah, if you've got a plus or a minus. Exactly. If you have a plus or minus outside parentheses, I'll talk about that tomorrow. Okay, so that's a phase shift. Okay, Brianna, what column always stays the same when you do a phase shift? Yeah, the Y's. Phase shift is going to move things left and right. It's not going to affect anything up or down. Okay, so I need my Y values. Yep, 1, 0, negative 1, 0, 1. Yeah, in the cosine column, you can read them backwards or forwards, or they're in the same order. 1, 0, negative 1, 0, 1. Those 5 are. So, okay, now we're going to take all the original x's. So Kristen, can you remind me what my original x's are for cosine? Same for sine as well.
0,
Yep.
pi over 2, pi, 3 pi over 2, and 2 pi.
And 2 pi. Okay, and Michael, what am I going to do to all of these values? Am I going to add or am I going to subtract?
Subtract pi.
Yep, I'm going to subtract pi. Okay, the first, the third, and the fifth one are pretty easy to do because they're not fractions. Okay, 0 minus pi is negative pi. How about pi minus pi? 0. How about 2 pi take away pi? Pi. You don't have to do them like that, but if you see some quick ones to do, you can get those done with. And now I got to do the other two. Pi over 2 minus pi. What's the denominator when there isn't one?
1.
It's a 1. Graham, what's my common denominator there? 2. So what would you multiply top and bottom by? 2. Okay, so what's 1 pi over 2? Take away 2 pi over 2. Negative pi over 2. Okay, and then the last one is same idea. 3 pi over 2 minus pi again. I need my common denominator again. 3 pi over 2, take away 2 pi over 2 is pi over 2. And that's your table. And there is the same pattern as we had last time, but you don't notice it because everything is reduced. But that's negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Okay? It's the same basic pattern as last time. Right, what's the last thing I have to do? Graph it. Okay, this time you need a little bit of room on the negatives, so leave a couple spots for negative pi over 2. You don't need to label 0, because that's the axis. Pi over 2 and pi. Sometimes the labels, you can kind of start to get in the way of each other a little bit. So this is 1. I don't really have a good place to put negative 1. Just squeeze it in there. And now graph those points. So we're at 1, 0, negative 1, 0, and 1. Okay. What I want you to be careful here is it looks like it's a V shape, but remember, here's your wave. What you're basically doing is sketching this section. So it kind of looks like a V shape, but it should have a curve to it. Okay? So it would kind of come in like that, come down, curve, and then it would continue on. You don't have to sketch the dotted lines, just that solid section. I just did the dotted lines to kind of get the flow of the wave. Okay, any questions on that one? Okay, so that's the second common shift that we do, okay, by pi. And the last one we'll do is shifting by pi over 4. right, so Devin, we know it's a phase shift because that's when you add or subtract in parentheses, but what column is going to stay the same? Yeah, we're doing a phase shift again, so the y's are going to stay the same. Wendy, can you remind me what my y values are for the sine function?
0, 1, 0, negative 1, 0.
Yep. So at least if you don't know anything else, if you can pick the right column to stay the same, you get 5 points just for writing that in. Okay, now, right, so I'm going to take all my x's. So I need to start with my original x's. Okay. What are my original x values for sine? That's the third one, so pi. Not sure. Kelsey, can you help her out? My original x's, they're the same for sine and cosine. Oh, Kelsey, sorry. Confusing me. Yeah.
What was it? What was the question?
My original x's.
Oh, just sine.
Yeah.
0, 5, 2.
Yep, that's good. And Kylie, can you tell me the last two?
I have it in degrees, not
What do you have for the last two in degrees?
270 equals 60.
Okay, so that is correct in degrees. Just make sure for the homework and test we'll always be using radians. Can somebody tell me what the last two are in radians? But those are correct in degrees.
3 pi over 2.
Yep. And 2 pi. Hey. And Gladdy, what am I going to do to all those x's? Am I going to add or subtract?
You're
I'm going to add, and how much?
pi over 4.
I'm going to add pi over 4. Now, this is one that I think after I do it 2 or 3 times, you're going to see the pattern. And we're not going to even have to do the last two. Okay, we'll just go by the pattern. James, what's going to be my common denominator for every single one of these problems?
8, 2, 4.
Yeah, one of those numbers. Yeah, common denominator is going to be 4. So if I want, you could put that in right now. They're all going to be 4. And the first one, 0 plus pi over 4. Pretty straightforward, pi over 4. Okay, how about pi over 2 plus pi over 4? What do I have to do first to add those up? Yep, make this 2 pi over 4. So I got my common denominator. What's 2 pi over 4 plus 1 pi over 4?
3 pi over 4.
Yep, we got 3 pi over 4. And then I think once we do one more, you'll see the pattern, I hope. Okay, common denominator again, James told us is, or Jim told us it's 4. So we're going to multiply top and bottom by 4. That turns into 4. That becomes 4. What's 4 pi over 4 plus 1 pi over 4? 5 pi over 4. All right, so looking at what's in that box, anyone think they can see the pattern?
7 pi.
Yep. So we got 1, 3, 5, 7. And the last one? 9. Okay, there's your pattern. If you don't notice the pattern, you could just do these out finding the common denominator, but that's what's going to happen. Okay, any questions on the table? All right, so last thing is we'll graph it. Okay, remember, these are all equally spaced. If you converted these to degrees, that's 45, 135, 225, 315, 405. It's just plus 90 each time. So, I'm going to put pi over 4 right there. Okay? What did I say that was in degrees?
45.
All right, I'm going to put it in parentheses because I want you to see something. That's 45 degrees. So how much of a gap is that right there? It's 45 degrees. Okay, that's a 45-degree gap. What did I say the next number is? 3 pi over 4. (135). Okay. In degrees, that's the next one. Where would 135 go on these grid lines? 2 more. Right? 135 would be right here. Why? Because if I put it here, what's this one? That's 90. Right? Each gap is worth 45. So if you put the next one here, now we've messed up. That's kind of like doing a number line like this. 1, 2, 6, 7. You weren't consistent. Okay, you skipped some stuff. So the next one is right here. Okay, that's 135. 45 and 45 away from the first one. Okay, so 90 away. Okay, the next one is right here. That would be 7 pi over 4. Did we have 9 pi as well? Yeah. So I just have to squeeze that one in. Okay, so it's important. I didn't space it evenly because I ran out of room, but it skips. Okay, sometimes that happens. If you're confused whether you should skip or not, that usually happens with the pi over 4s. Not so much with the pi over 2 and pi. Okay, and now just graph your points. So 0, 1, 0. I'm just going to have to draw it in the middle of my label. If I had thought about it, maybe I should have put my label up above rather than below, but that's okay. And there's your graph. Okay, so tomorrow we'll look at the next transformation, and we didn't have time today for me to play a phase shift, but I'll play it so you can hear what it sounds like. Okay, homework tonight will be a worksheet. Okay, I'll try to put the worksheet in the video, so if you lose it, the problems will be online as well.